Welcome to this breakout session presentation on interaction of HVDC systems and connected offshore wind farms under fault conditions. My name is Christina Brantl and I'm a research associate with RWTH Aachen University. I have the honor to share this presentation with Lee Xu, professor at University of Strathclyde. In this presentation, we will first present the impact of different fault clearing strategies at the offshore connection point and then go into detail on the implications of the requirements towards the offshore wind farms and their controls. Existing offshore wind farms are based on point-to-point links based on the symmetric monopolar configuration. So any fault on the HVDC system, be it a line fault or a converter fault, leads to a loss of the entire system until the fault is repaired, which might take several months in case of an offshore cable fault. So in case of any fault, there's an emergency shutdown of the entire offshore wind farm. In the future, multi-terminal HVDC grids are envisaged for the integration of large-scale offshore wind integration. And these multi-terminal systems allow fast resumption of power transfer from the offshore wind farm to the onshore AC system after fault clearing. For the fault clearing and DC systems, different clearing strategies have been proposed. Each of these comes with new requirements on the offshore wind farms. Within this presentation, we're going to first do an analysis of different fault clearing strategies and the resulting impact at the offshore connection point, and then go into more detail on the development of suitable control strategy for the offshore wind farm to allow a secure DC fault right through and fast resumption of power flow. In general, fault handling is a key challenge in HVDC networks. We need reliable and fast separation of DC faults, a limitation of the fault propagation, and the protection of the system components in case of a fault. And in general, the DC faults must not endanger the AC system stability, especially when it comes to larger HVDC grids. So there are different strategies proposed for these systems with new components, and I will only give a brief overview here. For more detailed presentations, I'd like to refer you to work package 4, 5, 6, and 10 on the different components and strategies. What's presented here is the strategies according to the Grid definition. And the first part would be the non-selective strategy, where the entire DC grid is one protection zone, so the entire DC grid is temporarily shut down and de-energized during the fault clearing process. Second option are fully selective fault clearing strategies, where every line is a single protection zone. So each line is separated by DC circuit breakers at each line end, which is very similar to the current protection design in AC systems. The third option is the partially selective option, where the DC grid is split into different protection zones, and each of these zones can have different protection strategies, for example, non-selective or fully selective one. The separation is done by DC circuit breakers as the protection zone interface. Within work package 2, a broad range of scenarios has been investigated, taking into account AC onshore faults, DC faults, and AC offshore faults, taking into account the different DC fault clearing strategies, topologies, and power flows. Within this presentation, we're going to focus on the impact at the offshore connection point. And to this end, I'm going to present first two fully selective implementations and two non-selective implementations. The first protection design presented here is a fully selective protection design with fast DC circuit breakers and corresponding inductors at each line end and based on half-bridge MMCs. The objective of the protection system design is that no blocking of the converters takes place. So during fault clearing, DC circuit breakers isolate the faulted line within a few milliseconds. The converters stay in operation and there's no impact on the offshore wind farm so that the power flow can be resumed fastly. Depending on the protection system design, a fully selective strategy might still lead to blocking of the converters during fault clearing, especially, for example, breakers with longer fault clearing times or smaller inductors are used, which might be done for having a smaller footprint of the components, which is especially relevant for the offshore platforms. In that case, to have a fast resumption of the power flow after the line has been resumed, an additional fast deblocking features of the converters is needed. So during the fault clearing, the offshore converter blocks, but still the DC circuit breakers isolate the faulted line within a few milliseconds. To then be able to achieve a fast deblocking, all the system parameters have to be back in their operational ranges. So, for example, the DC system voltage has to still be in the operating band of the DC converter after fault clearing, and also the internal current thresholds and submodule voltages have to be in an allowable band. In that case, the fast deblocking can take place. And this is typically achieved below 1 cycle, so then there's a transient effect on the offshore system, for example here shown in the AC voltage, below 1 cycle. Coming to the non-selective implementations of a fault clearing strategies, the first strategy proposed here is based on fault blocking converters with fault current control capabilities, for example based on full bridge submodules. And this enables us to reduce the capabilities of the circuit breakers at the line end so that, for example, residual current breakers can be used here. So in case of a fault, the converters control the DC fault current to 0 without loss of controllability on the AC side. When the current through the breakers on the faulted line is small enough, the residual current breakers can open, and afterwards a smooth transition to post-fault power flow via the HVDC converters can be achieved by first ramping up the voltage and then the power. However, during the fault clearing time, which might last over 100 milliseconds, no power export from the offshore wind farm is possible, so AC overvoltages could arise and a corresponding high voltage ride-through mode is necessary. For this last example, a non-selective strategy based on fault feeding converters, for example based on half-bridge submodules plus AC side circuit breakers is presented. This is the strategy that is also used for the existing point-to-point links. So during the fault clearing process, the converters block for self-protection, and this leads to a loss of controllability of the converter and a breakdown of the AC voltage. The fault clearing itself is achieved by opening of the AC side circuit breakers, which takes several 10 milliseconds in the range of 40 to 60. And then when the AC circuit breaker is opened, this leads to an isolation of the offshore wind farm from the DC system. So we have a non-defined status of the offshore wind farm in this situation. For recovery of the system, the offshore converter has to be recovered and the AC side circuit breakers have to be reclosed. And ideally, we would have a smooth transition to after-fault power flow from the offshore wind farm. So this is a very demanding situation for the offshore wind farm with a non-defined status in between. And this will be discussed in more detail in the following section.
In this part, the implications on the requirement towards the offshore wind farms, considering different DC protection strategies, are investigated. Start from the existing point-to-point HVDC connection system. In such a system, the offshore DC converter establishes the offshore AC system with voltage and frequency control, and any DC faults are likely to be permanent, which will lead to the shutdown of the entire system. So for existing offshore wind turbines, they usually operate in grid following mode. The active and reactive power are controlled in a similar way to AC connected offshore wind farms. There will be inner current control and current limiting capability during local offshore AC faults. In the event of DC fault, the main requirement is to facilitate safe shutdown of the system. When an offshore wind farm is connected to mesh DC network, as previously seen, remote DC faults may lead to the temporary loss of control of offshore AC system due to the blocking of offshore DC converters. Therefore, to facilitate rapid system restoration after fault isolation, offshore wind farms should remain connected during the whole duration of the DC fault transient. This adds to a significant new requirement for offshore wind turbines. Once the control of offshore AC system is lost, the offshore AC network needs to be maintained by the offshore wind turbines. Seamless transition of wind turbines between grid following and grid forming modes are required in order to maintain offshore AC voltage and frequency during offshore DC converter disconnection, and to facilitate rapid system restoration after fault isolation, supporting the start of the offshore HVDC converters. This shows an example of the control diagrams for wind turbines. The green blocks refer to normal operation, which contains the outer active and reactive power control and the inner current control. In order to maintain the offshore network when the control from the HVDC converter is lost, additional control functionalities are added as shown in the red blocks, so the wind turbines are switched to grid forming mode to control their own AC voltage and frequency in order to facilitate rapid system restoration after fault isolation. To give an example, a 4-terminal DC network is considered. There are 2 onshore and 2 offshore converters connecting to offshore wind farms. Partially selective DC fault protection, as previously described, is used here. So cable 24 is protected using DC switch, while cable 12 and 14 are protected using fast DCCBs. considering a pole-to-pole DC fault at cable 24 at 2 seconds, MMC4 is immediately blocked while cable 12 and 14 are isolated by their DC circuit breakers. However, cable 24 can only be isolated once it is completely de-energized. Now let's look the sequence and the waveforms at the offshore wind farm system. So the DC fault causes the AC voltage and power generation from the wind farm to quickly reduce to zero. The offshore AC circuit breaker opens and the offshore wind farm becomes islanded. So the wind turbines are switched to grid forming control as previously described, and the offshore system voltage is quickly restored. After the de-energization of the cable 24, the DC switch can be opened to isolate cable 24 from the offshore converter and the network. The offshore AC circuit breaker can then be closed and MMC4 re-energized. Cable 14 is then connected to the offshore system, and the normal power generation can be restored. So from this example, it can be seen that the additional wind turbine control functionalities help to maintain the offshore system during the DC fault transient and ensure fast system restoration after fault isolation. So this concludes our presentation. Thank you for your attention. For further questions, please feel free to contact us.
Welcome to this breakout session presentation on recommendations towards HVDC grid codes. My name is Christina Brantl and I'm a research associate with RWTH Aachen University. In this presentation, I'm first going to present the current status of HVDC grid codes and analysis of existing requirements at the AC point of connection, and then in the next step, I'll explain steps towards requirements at the DC point of connection. The starting point in promotion was the ENTSO-E network code, which is published as a Commission regulation on the official title Network Code on Requirements for Grid Connection of HVDC Systems and Direct Current Connected Power Park Modules. So from the title, it already alludes to that this grid code specifies the converter behavior at the AC point of connection, so including frequency and active power related ranges and control modes, AC voltage ranges, reactive power ranges and corresponding control modes, AC fault rate through and short circuit contribution. Is intended to facilitate the integration of single HVDC systems into the existing AC systems. So the existing AC systems is always the starting point, and the new HVDC systems should seamlessly integrate into the system. There are no specific statements on the DC side. Another thing is that the ENTSO-E grid code provides a broad range of possible specification, and this is intended to provide the basis for further refinement in corresponding national implementations. During the course of promotion, several national implementations have been published. The map on the right shows the current implementation status in the different countries around the Northern Seas. And within this slide, I want to present you the main outcomes of the analysis of selected examples of those national implementations that we did during the work of the work package. So first observation is that some aspects are specified in a very similar fashion in all the analyzed grid codes. So one example would be the AC fault rate through levels and the requirement of reactive power support during AC faults. Some of the aspects specified are then associated with different timings. So for example, the fast fault current contribution in the different national grid codes. What's also striking is that some national implementations exhibit a lot more detailed requirement than others. So there could be a fast fault current contribution only specified for symmetrical faults. But for example, in the German and Spanish grid code, there's very detailed requirements on how to specify the fault current also under asymmetrical AC faults. Some requirements are only imposed for some countries, for others not at all. So one example here is inertia provision. That could also be related to the number of HVDC connected power plants within those systems. And then some implementations specify the requirements taking into account converter capabilities, and some focus on the requirements from the AC system perspective. So for example, a power reversal is expected within a few milliseconds or seconds, depending on if you talk about what the converter should be able to do or is able to do versus what you would want from the overall system from a system perspective. What's common for all these national implementations is that the HVDC system are seen as separate single systems. So there's also no specification on an overall DC grid code here. And what's in general to be stated is, while there will always be a deviation of requirements at the onshore connection points due to the different system conditions, contradiction of requirements should be avoided to facilitate the development of multinational HVDC systems. And this is even more important when we look at the development of a multi-terminal system offshore, where it really has to be ensured that the requirements from the different national grid codes do not impede the connection of the different systems in the future. Having this in mind, in the following part, I'm going to present the results and steps towards requirements at the DC point of connection. To allow the development of multi-terminal DC grids, first, several normal operation and system design parameters have to be specified and aligned. So, for example, the DC voltage level, the DC configuration, the operational strategy, and of course, interoperability of the different components within the system have to be given. Moreover, it has to be defined how DC side faults and contingencies are treated. So what are the applicable reliability and availability criteria for those DC grids, and what is the impact of faults and fault clearing strategies on the overall system and the components? There is no standard fault clearing yet, and this leads to different options also within the grid codes how to define the DC fault right through, for example. For future offshore grids integrating several gigawatts of offshore wind farms, it has to be sure what is the role of the offshore wind farms. So, for example, with regard to their control capabilities for AC and DC fault right through, the use of grid forming controls within these offshore wind farms, or the use of for black start of the overall DC system. The fourth part that has to be taken into account is the AC system dynamics. With the DC systems becoming larger and larger, it will be more important for them to provide auxiliary services to the AC system, also vice versa. And the overall AC fault right through of the system has to be ensured, and also when connecting those larger DC systems to different synchronous zones, it has to be ensured that the different frequency reserves are respected or accordingly changed. So overall, there's a broad range of possibilities to design those DC grids, different with different control features, different configurations, specifications, and criteria. And there's not yet a standardized DC system. So coming from this, let's see what a DC grid code would require. In general, a DC grid code should be discrimination-free to ensure interoperability between the different components, but also between different vendors connected to the system. Ideally, it would be plug and play, and it should not inhibit the technological development, because in general, the HVDC technology is still under development. So requirements on the grid code are that it gives functional requirements at the point of connection for the converters, AC point of connection and DC point of connection, and it should find a balance for different solutions and the system requirements. When trying to specify corresponding HVDC grid codes at the DC point of connection, we run into several challenges. So first, let's have a look. What was the basis for AC transmission system grid codes? In general, that was a given system voltage and a given grounding strategy. Was the known passive behavior of generators under faults, allowing the system operators to define corresponding AC fault right through profiles, for example. And there are standardized fault clearing sequences and components. When looking at the planned and existing DC systems, there's a range of DC system voltages applied. There are different configurations, so for example, symmetric monopole configuration and the bifault configuration would go along with different grounding strategies, leading to different behavior under fault conditions. And then the converter behavior and capabilities depend on the converter type and the associated controls. Overall, there's a lot of control systems involved, for example, also in the offshore wind farm, and there have been several interactions identified between those systems. Moreover, there are different fault clearing strategies proposed for the DC systems, leading to different possible DC fault right through profiles. So as shown in the bottom picture here, for a strategy based on DC circuit breakers, the left profile might be applicable with a certain DC circuit breaker opening time, but when applying, for example, fault blocking converters with a fault current control capability, the profile might rather look like on the right side. So it's very difficult to specify a generic DC fault right through profile which would be applicable for any grid code. Having in mind the broad design possibilities for future HVDC grids and the just discussed challenges with regard to designing an HVDC grid code, there are still several steps needed to allow for future HVDC grid codes. In general, key aspects that facilitate the interconnection of HVDC systems in a multi-terminal DC grid are same DC voltage levels and ranges, and having the same system configuration. With regard to the protection, a suitable definition of protection zone boundaries and the respective protection strategies and DC fault right-through requirements in each zone need to be defined. Moreover, there needs to be a wider system perspective on, for example, power balancing capabilities and duties of connected converters. For example, when it comes to energy balancing and frequency support, the required energy has to come from somewhere and has to be defined if this is from an offshore wind power plant or a connected asynchronous zone. While there's no DC grid code available, the integration of several DC systems needs a lot of studies, for example, EMT studies, interaction studies, hardware-in-the-loop control studies with replica system, to ensure that there's no detrimental interaction between the systems. So while there are possibilities to bridge that gap, while there's no DC grid code allowing the least detrimental actions there could be, to design a future HVDC grid code and understand how those interactions between the control systems, for example, arise, there's further analysis needed with regard to those specific control actions, and also the influence of the DC grid design and the status on the control parameterization. So how influential is, for example, taking out one of the lines or turning off a converter to the overall control parameterization and interaction. There are furthermore suitable ways needed to specify requirements on the control to limit those interactions. And also, this is specifically a case for the DC side, but also for the AC side. So there's always a close interaction between the AC and DC side, especially under transient and contingencies. So there also needs to be an interaction and stability analysis of the integrated AC-DC power grids and their respective controls. So there are still a lot of challenges on the way towards HVDC grid codes. Within promotion, a lot of studies have been carried out showing that in general the control and the interaction between wind farms, the DC grid under different fault scenarios is possible, and that there are concepts to allow the system to work fine. But to define it in a general way in an HVDC grid code is a next step that still needs further research. Thank you very much for your attention. For further questions, please don't hesitate to contact me, and you can also refer to the deliverable D2.4, which summarizes all the aspects on the grid codes that we analyzed. Thank you very much.